All right, so I hope you all enjoyed your lunch. Up next, we have Klara Mundilova and Michele Vidulis, who are going to tell us about geometric fabrication with CodeNets.
Thank you for the introduction. I'm Klara, and this is Michele. We're affiliated with the EPFL's Geometric Computing Laboratory, and we're going to tell you something about our recent work on the geometry and interactive design of CodeNets. Many materials, such as paper, aluminum, or even a thin sheet of woods, come in sheet form. And a major advantage of these sheet materials is that they can be processed with two-dimensional tools like CNC milling or laser cutting, which is significantly simpler than 3D counterparts. After such an initialization manufacturing step, these sheets can be bent into three-dimensional forms that can then be even joined along seams to create even very complex structures. Because these shapes are relatively easy to manufacture, they have applications in many different fields, ranging from architecture, art, design, to engineering. In this talk, I will talk about our recent contribution to a family of piecewise developable shapes, namely CodeNets. And this project was motivated by the following observation, that when we take individual sheets of paper, they are quite flexible, but when we join them together into these tubular shapes, they become quite stiff, while being still very lightweight. So, for example, this table holds, I think, almost 6 kilos of water, and while weighing still just like the weight of the material, which were like 80 grams. Yeah. So in this talk, we will first provide a background on developable surfaces. Then we'll show how multiple developable patches can be joined into more complex shapes, and we will highlight their connection to differential geometry, the smooth and discrete. And then finally, we will build on these foundations and present our recent work on the theory and interactive design of CodeNet. We will highlight the construction, then how our implementation as an interactive design tool, and then provide an overview of our numerical optimization approaches. Okay, so let's start with the first part on developable surfaces. It's really hot here. Okay, so a developable surface is a surface that can be flattened into the plane without stretching or tearing. And in this presentation, the theory is mainly motivated by the observation that smooth developable surfaces contain a family of lines, the so-called rulings. Lines. Surfaces that are composed of one parameter of a family of lines are also known as ruled surfaces, and these lines are also called the rulings. Intuitively, a ruled surface can be obtained by tracing a line in space along a curve. It is important to note that not all ruled surfaces are developable. And this developability, the local developability of a ruled surface, depends on the tangent plane, or on the behavior of the tangent planes. Just as a small recap, the tangent planes, or a tangent plane to a surface in a given point, is the local best linear approximation of that surface in this given point. And a tangent plane is spanned by the partial derivatives of the surface parameterizations. And in the following, we will abbreviate them by SU and SV. So when we look at the behavior of tangent planes of points along a ruling of a ruled surface, we observe two cases. In the first case, the tangent planes rotate along the ruling of this ruled surface. And in the second case, this orientation can stay the same. And in that case, this ruling is also referred to as a torsal ruling. It is a special case, and surfaces that are composed of torsal rulings are also referred to as torsal ruled surfaces, or TORS for short. Torsal ruled surfaces play an important role when it comes to the developability. The following is a known statement from differential geometry, namely that a torsal ruled surface is developable. In the context of this mini course, there is not enough time to provide the proof or the background, but we would just like to leave you with this intuition. So in a neighborhood of a non-torsal rulings, the tangent planes like rotate, and because of this rotation of the tangent planes, there is like local stretching or compression. In the neighborhood of a torsal ruling, on the other hand, we have only like local bending behavior. We have two models that we brought with us. I will pass them around later. So the first case is the non-torsal ruled surface. And you can see that I'm struggling to really align a piece of paper around here, and this is due to the property of the like rotating tangent planes. Michele, thank you. And in the other case, we have a surface with torsal rulings. And here you can see that I can like nicely move around the piece of material or the piece of paper around the surface, which is a good indicator for developability. Okay, so there are some well-known examples of developable surfaces. Cylinders are characterized by parallel rulings. Cones are characterized by rulings that pass through a single point, also referred to as the cone apex. And then there is a third class called tangent developable surfaces, where the rulings are the tangents of a space curve. The space curve is also called the edge of regression, here depicted by red, and it contains the singularities of the surface. Therefore, in most applications, one tries to only work with patches that are far or like not too close to this edge of regression. Yeah, and these three surface types play an important role because every smooth developable surface can be decomposed into one of these three types plus the planes. So this is an example of a smooth developable strip. And now these are the rulings that correspond to the strip. And if we extend them, we can like distinguish between the three cases. So going from the left to the right, we have tangent developables to the left with the edge of regression highlighted in red. Then we smoothly or tangent continuously transition to a cone with the cone apex highlighted in red. Then there's a planar part, and then there's a cylindrical part. And here you can see that it can also happen that the edge of regression, like at some point, passes through infinity. So here, oh, you cannot see my cursor. Can I point with this? So it starts over here, but then it like moves over here, and then it like reappears on this side, and then it just like goes further up and to the right. Yeah. So again, the justification of this statement goes a little bit beyond the time frame that we have here, but we would again like to support this claim by the following intuition. So smooth developable surfaces or smooth developable strips are have discrete counterparts, namely strips of planar quads, because they also can be unrolled into the plane without stretching or tearing. So you can just place a PQ strips like planar quad by planar quad. Here we will consider triangles as a degenerate case of a planar quad. And now if we locally look at the behavior, oh yeah, and the interior edges of this PQ strip, those are the discrete analogs of the rulings. And if we look at the behavior of three consecutive rulings in a PQ strip, we can distinguish between two cases. So either they have one common intersection. In this case, this would correspond to either a discrete cone or a discrete cylinder, depending on whether this common intersection is a point at infinity or not. I think I said it the other way around, but yeah, I hope you know what I mean. Or we have two distinct intersections. And in this case, we can think of the intersections as being part of a polyline. And then the extensions of this polyline, the edge extensions, those correspond to these discrete rulings, and one can think of this polyline of being the discrete counterpart of the edge of regression, because these extensions correspond to the tangents of this polyline. Yeah, so I hope this is now like a little bit more intuitive, that there are really only these, like locally, these three parts if you have sufficient smoothness. So discrete cylinders, cones, or tangent developables. Okay, so to conclude this section, we have a little bit of a trick question for you, and I'd like to let you briefly think about this. So, do you think that we can bend this square piece of paper into a torus? Okay, it's hot. So I'll just continue. So the answer is theoretically yes. So for those of you who are thinking back of what I said about like torsal ruled surfaces being developable, I would like to highlight that this statement is only valid in one direction. So it essentially means that if we have a torsal ruled surface, it will be developable. But it doesn't go the other way around. For the other way around, we need more smoothness assumptions. And in fact, there is like the famous mathematician John Nash found that there is even an isometric embedding of a flat torus into three-dimensional Euclidean space. So in other words, there is a way how to bend a square of paper into a torus shape without stretching or tearing. But yeah, only very recently Borelli and co-authors actually visualized and wrote an algorithm of this fractal shape that would correspond to this torus. So this is a C1 embedding, meaning that at every point there is a tangent plane, but it's not curvature continuous. And this is where, like, yeah, this is what they're exploiting here. Okay, so with this, I would like to transition to the next part about the combination of these piecewise developable shapes. Okay, so combining multiple developable shapes unlocks a wide range of possibilities. Examples include, for example, approximations of freeform surfaces, such as these highly functional boat hulls, or tubular shapes, exemplified here by an art piece by Korean artist Sang-soo. Here, what I find very remarkable is that even joining two pieces of very simple regions, like two ellipses, already results along their boundaries results in complex three-dimensional forms. And in the special case of two shapes, or like these forms were recently these forms were can be attributed to Tony Wills. And are also referred to as D-forms. Okay, in the special case where we can also get compositions of developable surfaces by creasing along a curve, and the special case is also referred to as a curved crease origami. And here, even a single curved crease can result in quite complex shapes, like this art piece by Dux Koschitz. More complex examples, like this spiral tessellation by Ekaterina Lukasheva, are quite intricate. This is just a variation of one of her designs. There are other also well-known personalities in computer science, such as David Huffman, who was exploring the behavior of paper by looking into compositions of conic creases, and also a very influential design which I find very remarkable, is this piece dating back to the Bauhaus, where students of Joseph Albers folded concentric circles in a pleated way, resulting in this hyperbolic shape. Okay, so to support the design of piecewise developable shapes, in a geometry-informed way. We borrow concepts from differential geometry. So in the following, we will talk about special surface parameterizations, the so-called smooth conjugate nets. And a conjugate net is a surface parameterization that satisfies this property, namely that the first partial derivatives and the mixed derivative of a surface parameterization are linearly dependent. A more intuitive interpretation of this is that along one parameter family of lines, or along both, but yeah, let us take one parameter family of curvature of curves on the surface in u direction. Then if we take the derivatives in the other direction, then this will trace out a developable surface. And this surface is also referred to as a tangent developable surface, or as a developable tangent surface, sorry. And this holds in both directions. The constraint is symmetric. And due to this local developability conditions, smooth conjugate nets have a discrete counterpart that are planar quad meshes, essentially being developable in a discrete way, again, in both directions. And when we do one-directional refinement, what we get is compositions of strips, of developable strips, or developable patches here. And those are also referred to as semi-discrete conjugate nets. So due to the versatility and ease of fabrication, developable surfaces and composition of developable surfaces have been a popular research topic. There are multiple modeling approaches. There are works that look into discretization-based approaches where shapes are modeled as PQ meshes, where the edges of the mesh are aligned with the rulings. These approaches have a little bit of a drawback that, like, with rapidly changing rulings, this becomes a little bit harder to tackle. And especially if you look at the developable patch, which I should have preferred, like maybe this one, then like there are like infinitely many possibilities how to like position this patch with the same ruling layout in space. But if you move it freely, the rulings will change, and you might end up having rulings that go in the very opposite of your initial ruling direction, and this then requires special treatment. And so to address these limitations, there have been other approaches. So, for example, triangle-based meshes, here exemplified by the stripified body by Stein and co-authors, used a variational approach to drive a triangle mesh into like this piecewise developable shape. And also here, a method to then retrieve the rulings from this discretized shape was presented recently by Verhoeven and co-authors. Other geometry-informed discretizations include checkerboard patterns and discrete orthogonal geodesic nets. And then there has been some work on genuinely smooth representations, for example, by Tank and co-authors. But also here, when it comes to preserving the isometry between the 3D state and the 2D state, the authors here require like some form of discretization to enforce this isometry. Oh, yeah, sorry. And so in this presentation, we will mostly focus on the first discretization approach, where we focus on PQ meshes, where the edges of the quads are aligned with the rulings of the mesh. And I'll let Michele take over.
Okay, so do you hear me well? Yeah. So hi everybody, I'm Michele from the Geometric Computing Laboratory. Very happy to be here. Thanks for the invite. So we were looking at the top block here, developable surface discretizations that use planar quad meshes. Let me do this. And now, okay. So in particular, when the developable patches have a regular arrangement, like in these split structures, it is natural to think about the strips as being generated by a polyline, so a set of rulings, swept and deformed in space. Okay. More in general, many common surface classes can be generated by considering two curves and sweeping one along the other according to a specific transport and modification rule. We will call the first curve, the one defining the path, directrix, and the second, the one being swept, generatrix. This specific surface here is of the simplest kind, and it is a translational surface. The transport rule is then simply a translation of the generatrix along the directrix. In this case, we could swap the role of the two curves and get the same result by translating the second curve along the first. The smooth surface, resulting from these two smooth curves, is a conjugate net in the sense explained earlier by Klara. If instead of considering a smooth directrix and a generatrix, we replace them by polylines, we obtain a discrete translational surface. Since this is the discrete counterpart of a conjugate net, it is a PQ mesh, as we've seen. Here are some more examples of surface types with one of their smooth conjugate parameterizations and the discrete PQ counterpart. We have scaled trans surfaces that are generalizations of translational surfaces in which, as the name suggests, the generatrix can also be scaled during the sweep. Munch surfaces are a bit different because the generatrix is kept in the plane orthogonal to the directrix and swept without twist along the directrix, according to a rotation minimizing transport. We will discuss them more in detail in just a few minutes. While rotational surfaces are obtained by rotating a curve about a fixed axis. During the rotation, any point of the generatrix traces a circular arc, and in fact, we can also interpret rotational surfaces as Munch surfaces in which the directrix is a circular arc. In all these cases, we can generate also two types of semi-discrete hybrids, where one curve is smooth and the other one is discrete. Note that while all these smooth surfaces are in general doubly curved, so not developable, the semi-discrete counterparts are always composed of developable patches. To summarize, the design of composite developable surfaces as PQ meshes can be broadly categorized in two main paradigms. First, we have optimization-based methods, which start from an initial mesh and iteratively adjust its geometry to obtain approximately planar faces. And then we have constructive approaches, which guarantee phase planarity by construction by leveraging geometric principles. Optimization-based methods instead typically provide only approximate solutions and may suffer from convergence issues. However, they offer considerably greater design freedom and can accommodate a wide range of constraints and objectives. Moreover, constructive methods naturally support one-dimensional refinement, making them particularly attractive for multi-scale modeling and fabrication-oriented applications. A natural question is then how to increase the design flexibility of constructive approaches while preserving the other beneficial properties that they provide. Now back to the four classes of surfaces that we have just introduced. We can now analyze their relationship in the discrete case, so the one we are looking at right here. Rotational and translational surfaces are different sets with non-empty intersection. Think, for example, of a cylinder that can be generated by translating a line segment along a circle. Both these classes are proper subsets of scaled trans surfaces, with rotational surfaces that are also a proper subset of Munch surfaces. We have just seen how they correspond to a rotation minimizing sweep, so Munch, of a planar curve along a circular arc. It is interesting to think about the type of developable patches that we can have in these PQ meshes. So for example, if we look at translational surfaces, we can only have cylindrical developable strips in both directions, while rotational and scale trans surfaces also admit cones in one direction, while remaining limited to cylinders in the other. The developable strips of a Munch surface instead They are different, and they can be of any type in one direction, but are limited to cylinders in the other. So a natural question here is how can we extend this construction, Monge, to support conical strips in practice, and in practice expand the design flexibility that we have with Monge surfaces. This brings us to discrete cone nets, which is a class of PQ meshes that exactly consists of cylindrical or conical strips. Cone nets encompass all the 4 surface classes that we have seen before as special cases. Just before moving forward, a quick note of caution, because cone nets have a similar name but should not be confused with conical meshes, where conical meshes are quad meshes in which the 4 faces meeting at a vertex are tangent to a common cone of revolution, which is here shown in yellow on the right. In the case of discrete cone nets, instead, the cones are the ones showed in the exploded view that are tangent to a strip formed by an arbitrary number of adjacent quads. So we're talking about different constructions. Recent work by Killian and co-authors studies smooth and discrete cone nets from a theoretical standpoint. Specifically, smooth cone nets are conjugate nets in which one family of tangent developables are not just any developable surfaces, but specifically cylinders or cones. Now, we might ask ourselves how general is actually this class of surfaces, because we have seen that discrete cone nets are a proper subset of discrete Monge surfaces that can only have tangent cylinders, but how much freedom does using tangent cones actually buy us? It turns out that it does buy us a lot of freedom, and in fact, Killian and colleagues show that every surface can locally be parameterized by a cone net. So this is really every surface locally is a cone net. We will not go into more details here, but an analogy that the authors use to make this concept more intuitive is the one of a point light. So if we think about a point light source, the light cone made by the rays connecting the light with the silhouette is a tangential cone in our sense, and moving the point light along a space curve will yield a one-parameter family of silhouettes which form the V parameter or U parameter curves of a cone net. A light at infinity, as we see here on the right, corresponds to a tangent cylinder, which can be considered a cone with an apex at infinity. In the following, we will present some of our contributions to the study, design, and optimization of cone nets. We will first review our novel cone net construction, and later we will show how this construction unlocks the design potential of cone nets with an interactive design tool for Rhino Grasshopper, of which Klara will give a demo in a few minutes. We will start by presenting the cone net construction. We will then show how this construction can be used for interactive design, and conclude by discussing some numerical optimization results and mentioning future research directions. I will now introduce the construction step by step, showing how cone nets can be interpreted as generalized Monge surfaces. So let's start. For a Monge surface, we need 2 ingredients, a directrix curve and a generatrix curve. We consider discrete polylines here for the sake of clarity, and because we are interested in design with discrete PQ meshes, but just be reminded that all the upcoming constructions also have a smooth counterpart. We define the support rulings as the segments that connect each generatrix vertex to the first directrix vertex. Because here with the projector is a bit faint, but there are lines that connect the center dot to the vertices of the triangle. So now if we sweep these segments along the first tangent edge, this is also a bit faint, but you can imagine that this generates a cylindrical extrusion that we intersect with what we call the bisecting plane at the next vertex to define the new support rulings. So there on the right, there is a plane visualized in 3D, and here we see the top view, and the plane cuts through orthogonally. So it's just a line. That's what we call the bisecting plane at the vertex, which is the unique plane through that vertex that makes equal angles with the 2 incoming edges of the directrix. These 2 properties, so the fact that all the support rulings belong to the bisecting plane and that the extrusions are cylindrical characterize the Monge construction. We also note that the swept quads have parallel edges, and that means that they are planar, or PQ. By sequentially propagating the construction forward, here, again, unfortunately, it's hard to see, but we eventually obtain the complete support strips. So here we can imagine seeing 3 strips, or each made of 3 adjacent planar quads. And due to the use of bisecting planes, adjacent quads in each of the strips are, I think it's really might really be the projector who's bumping up the highlights. Because also the bars here are a bit faint. But okay, trust me, there are some planar quads there. And adjacent planar quads share the same angles. And this is a property that is inherited from the use of bisecting planes at vertices. This, again, this discrete construction corresponds to a rotation minimizing rigid sweeps, which means that all the orthogonal cross-sections remain the same along our surface, and this is, in the end, the Monge surface that we can extract by connecting together our support strips. Okay, now how about generalizing those 2 properties? Let's start from the use of bisecting planes. So property 1, here you can see what happens if instead of using bisecting planes, we let those planes vary freely. So here, each support ruling can be independently controlled via an associated family of planes that can now be arbitrarily tweaked. The additional freedom gained by choosing arbitrary planes becomes clear also by looking at the support quad angles. So here it's more clear to see now that are not anymore bound to be the same. So here we have different angles across the rulings. The surface then can be extracted exactly as before. So we take the support strips, we connect them together, and we get, again, planar quads, but the difference now is that the cross-section of our surface is not preserved and can, in principle, vary along the sweep. So controlling this cross-section, the difference here might be subtle because we're using just a triangular cross-section, but imagine a more complex polyline. The cross-section can change wildly, and controlling it can be challenging. So what we want to do here is we want to generalize also the second property to give us a bit more control of that shape. Okay, before proceeding, let's quickly zoom out and check where we are. We started from a Monge surface and used arbitrary planes to obtain the current ConNet, which is a more general surface, but remains limited by the cylindrical shape of each of its sections. Our next goal is then to push the generalization 1 step forward and access the whole set of discrete ConNets. So, consider now the individual cylindrical sections that we started from. And now, instead of being limited to cylinders, imagine you can use cones. This is exactly what ConNets do. Cones encompass cylinders as a special case. So we can see here at the center, we are still using a cylinder. However, the problem with cylinders in this context is that they can also pose a challenge because the corresponding apex escapes at infinity. So numerically speaking, explicitly modeling the apex position is not a great idea. In a minute, Klara will tell you more about an alternative way to encode the surface that completely sidesteps the need for explicit cone apices. So now with this second generalization in place, the discrete ConNet construction is now complete. We will later discuss some more of its properties, but now back to Klara, who will tell you more about the apex locating function.
Skip it here. Thanks, Michele. So, as Michele mentioned, we'll look at the cone construction in greater detail. It is happening sequentially. So, starting from an initial generatrix and directrix, we first deconstruct the planes that are spanned by the first edge of the directrix and points on the generatrix. And to proceed with the construction, we need to determine these edges that correspond to those cones, as mentioned by Michele, and we want to have influence over these edge directions. So how do we do that? This straightforward approach with just evaluating these cone APCs or using the cone APCs to evaluate these edges is requires special treatment of like cone APCs that are far away and cylinders. So what shall we do? And so coincidentally, during my PhD, I was involved in a project with Professor Eric Demain from MIT and Professor Tomohiro Tashi from the University of Tokyo. And in this project, we were looking into ways how to take a globally developable planar quad mesh that corresponds to a very coarse curved crease design, and how to constructively turn this into an approximation of a curved crease design. To do like interactive exploration of curved crease origami. And the main idea of our algorithm was to replace each planar quad in this coarse mesh by a smooth or coarser, like more subdivided cone. And those cones would then be tangent continuous along those strips that would correspond to like developable surfaces or finer developable strips, PQ strips, while in the other direction they would be joined by globally developable vertices. So the construction would take this coarse mesh and then turn it into a finer mesh that would still be globally developable just by linearly evaluating like each vertex or each ruling at a time. So similar to here, we found that our computation of those creases would become numerically unstable for cones where the cone APCs would be far away. And to address this issue, we instead of using the cone apex, we turned to scale mappings. So specifically, we used scale mappings where the scale center would correspond to the cone apex. And instead of encoding the scale mapping with the scale center, we would encode the scale mapping with the scale factor that would determine the scale center. And if you're interested to learn more about this project, I invite you to check out our last year's Advances in Architectural Geometry publication. Okay, so I would like to take the time and briefly discuss the main idea here. So suppose we're given 2 points, A and A bar, and we want to find a scale mapping that maps A to A bar. Again, as mentioned, we don't want to use the scale center, but we know that it will be contained on the line connecting A and A bar. But we also want to use the scale factor instead. And to determine how to obtain the scale mapping, we will look at its how it acts on a point P. P here is depicted in the 2-dimensional plane, but it holds also for higher dimensions. So first we'll look at the vector connecting A with P. And we'll multiply it with the scale factor, in this case lowercase a. We can now move this vector, or add this vector upon A bar, and define the resulting point as the image of P. And it turns out that this corresponds to a scale mapping, and in the special case where A equals 1, this will become a translation by A bar minus A. We can also see that this how this mapping acts upon a point P determines also the location of the scale center V. And yeah, you can see in this case it's over here. So now, given 2 points, A and A bar, we might ask how to determine the location, or which A, like how does this lowercase a, the scale factor, influence the location of the scale center? And for this, I plotted the new axis here. And we will look at different locations. So in this or like in the sketch, the scale factor corresponds to approximately 1.5. So it's somewhere, it's greater than 1 because like 1 would correspond to a translation, and it's less than infinity. If the scale factor would be greater, like as a, I should point with this one. Oops, no. As the scale factor increases, we like this vector will get bigger, and we will move towards a over here. And yeah, so therefore, this area over here corresponds to values that are between 1 and infinity, because I cannot see the laser anymore. No, yeah. Sorry, but as we approach 1, this cone apex will move towards infinity on the left-hand side. Eventually returning on the other side, where for values that are between 0 and 1, the yellow vector is much bigger than the green vector, and therefore the scale center will be on the other side. And for cases between 0 and minus infinity, or for negative values of a, we actually become this, we have this flip of values and scale centers that would be between a and a bar. And so in the first formulation of our construction, those are the undesired cases, because we don't want this local flip, because this would correspond to flipping quads in our construction. So what we can now do, instead of evaluating these edges from cone APCs explicitly, is that we can take the last generatrix aligned polyline, scale it up with like the scale factor that can be specified by the user, and then determine these like edge directions from this scaling. So for actually a full like conet, we need a user can specify a scale factor for each parameter t, when we think of t as being the discrete parameter that parameterizes the directrix. And so, for example, this shape will then get like a discrete set of values that we plotted over there, and we will refer to all these scale centers to this list of scale factors as the apex locating function. Here, this slide shows 2 more examples of a little bit wilder shapes. You can see that this encoding captures like smooth looking and like not so smooth looking shapes, and quite robustly, because like all these scale factors, or this apex locating function, is around 1 in both cases. Okay, so before transitioning to the next subsection, I would like to briefly talk about the motivation behind the terminology support strips from this construction. So one important application of meshes with planar faces is in architectural geometry, particularly in the design of glass and steel structures. The physical realization of such structures requires structural support that is oftentimes done by aligning beams along the edges of this mesh representation. But this aligning of beams is challenging at nodes where multiple edges come together. And this node complexity can significantly increase the costs of the manufacturing costs of the project. So these geometries that have like this well-aligned beam structures, those are of theoretical and practical interest. Here we follow Pottmann and co-authors, who introduce the term torsion-free support structures. So according to them, a support structure of a mesh consists of a set of node axes that are lines that pass through the vertices of a mesh. And a support structure is torsion-free, or is defined to be torsion-free, if adjacent node axes that share an edge are coplanar. And and now we'll show how the torsion-free support structures are just like, can be extracted directly from our construction. So first recall that our support strips of the constructions consist of planar quads. So here the polylines of the mesh are connected to the directrix. And then in the other direction, these connections between two rulings of the support strips are also coplanar because they meet in a single point that is located on the directrix. So therefore, this rulings of our support strips are can be used to extract torsion-free node axis directions for free. What we can also do is we can apply our construction to non-manifold generatrices, and this will give us, or this enables us, the generation of complex, multi-layered structures that also have planar faces by construction. Okay, and I think now we reached the point where there's, I think we're halfway through. Do you have any questions? Okay.
So thank you both for the talk so far. You said earlier that any surface can locally be parameterized as a cone net, but how locally does it have to be? Because if I think about some very complicated surface, the silhouette is not going to give me information about parts that are hidden, right, or occluded.
Yeah, that's a good point. So in this example that we showed here, what can happen is that if you follow this construction, is that those silhouette curves will intersect quite easily, and this is also why, for example, this curve is chosen in this way. It is quite weird, so that it's a nice alignment and a regular penalization. I think we don't, at least I don't have a notion how local this construction is, but...
So I could imagine for convex surfaces, maybe you can cover the entire surface. Is there a more general class of surfaces for which this is true, that you can find a global cone net of them?
At this point, I don't think the audience give any hint on how local.
Yeah, but in the second part we will show a bunch of examples. So we will also show saddle-shaped surface and different shapes that are cone net parameterized, that correspond to discrete PQ meshes that are cone nets. So it's not only limited to convex shapes, but yeah.
Yeah, I guess about the size of the neighborhood, we just don't have an answer. But you will show, you will see a few more, maybe more exotic shapes in a sense, coming up later on, that are not all of these complex looking.
Mm-hmm. Yeah. Cool, thank you.
Hi, so my question is maybe a bit more open, but I wanted to say it now before we move on from that application, because I think I can see how like flexible your method is for the application you have of constructing like glass panes or things like that. But for applications of like industrial design where you have a sheet of metal and it's easier to just like deform it to form a curve, how do you think your like kind of framework adapts to generating surfaces that are parabolic or cylindrical without going through like those supporting patches?
I guess part of the answer will also arrive in the demo that Klara will do in a second, showing how to interactively design these surfaces. I would say like a reasonable default that we start with is always the munch construction, for example, where you can easily recover a cylinder, for example. Right? So in that case, it's in some sense it's a subset of what we do, and that can be easily parameterized and obtained. In fact, as the default of our plugin. And then from there, you can apply variations that we try to make as intuitive as possible from a design point of view. But maybe we'll get there soon. Feel free to re-ask the question again later.
Okay, thank you.
Okay, firstly, I want to thank you for those examples, like aesthetically beautiful for decoration. Nice. My question is that in last parts you mentioned about architectural parameterization and physical realization. So in your method, flexibility of having laminar sheets and enabling the stiff designs at the end when assembled, I was wondering factors such as topology with affects the stiffness of the design has been integrated in the cone net representation, or one should, like, it's an open question.
Yeah, so we do have some initial explorations towards not only tubular structures, but into networks of structures that are of cubes and like other shapes of like combinations. But yeah, like this is something that we would hope to explore in future work, to like go into like structure properties. I think Michele will conclude the talk even in this direction. Oh no, no, I spoiled. And I will hopefully show you soon an application of like a structural frame that uses a closed topology. Yeah, but yeah, possibly future work. But a very good question. Do you have something to add to that? Oh, yeah.
Hi, just two quick questions. So you talked about the torsal ruled surfaces.
Yeah.
And they imply that they're developable. And the discretization of the torsal ruled surfaces gave rise to the PQ strips.
Yeah.
But then later on you said that's equivalent as to the developability of this.
Oh, yeah.
So, like, are you looking at developable surfaces or only at like the subset of torsal ruled surfaces, or?
I hope the recording will show that I didn't forget to say that I'm looking at smooth developable surfaces, and I hope this should be covered then in technical correctness. Yeah, thank you for pointing this out. Yeah, again, at that point I was talking about smooth developable surfaces, and if one has at least C2 smoothness, then those two statements are equivalent. Then a surface is developable. Yeah, if and only if it's a torsal ruled surface.
Thanks. And then the other question was for the support rulings. When you generalize the Monge construction, you only change the planes at the vertices, or as you rule along the directrix? Like, are you like interpolating, or?
Yeah. So we'll see that multiple constructions can lead to the same cone net. So there is like this huge, or it's a bit of an over-parameterization. So technically you could also change like the curve you're starting with, but I hope that this demo will show that it's like kind of intuitive to just start from this Monge construction and then like generalize it from there.
Okay, cool.
or I can just like, give you this microphone.
on the construction that you saw with the low-res polyline in particular, the planes always go through the vertices. Yeah, because that's the fully discrete construction. As I mentioned, there are also the smooth equivalents of those constructions that we cover in the first paper I show that was published at SIGGRAPH last year. And in that case, Klara worked out all the equations for the smooth construction and then the discrete version as well. Yeah. Okay, then I'd say maybe we can continue.
Yeah, sure.
Keep your other questions for later.
So the next part, in the next part, I'll talk about the interactive design. So in the previous parts, we've seen how to get from like this input, the set of inputs that we discussed of generatrix, directrix, like a bunch of input planes and apex locating function through our construction to an like conet. But now I want to share some insights about why just taking like this implementation for design might be a little bit impractical. And I'll in particular show how we adapted this construction as a interactive plugin for Grasshopper Rhino. And yeah, this is what I'll do now, and I hope it will work. Okay. Yeah, I will need to exit presenter view. Okay, so yeah. Good. Okay, so for those of you who are unfamiliar with Rhino, it's a CAD software that is commonly used by architects and designers. This is the Rhino viewport, where one can generate geometries and work with them and visualize them. And here, this is Grasshopper, which is a scripting environment, a visual scripting environment that I think with Rhino 8 comes naturally. It's already part of Rhino. It started as a standalone project, but now it's incorporated into Rhino by default. So here in this visual scripting environment, variables and methods come as nodes. So here this one corresponds, for example, to a point. And methods can also correspond to different nodes, and one can connect these nodes via curves. And so what we implemented is a plugin that can be downloaded from my homepage and maybe through EPFL homepage as well. For free, and you're welcome to check it out. And the current state of it looks like this. So this, the current CNets or CNets implementation encompasses multiple components that generate geometries, and I'll show you some of their functionalities. So the main component is the CNets construction, as you might have guessed. Starting from a directrix, generatrix, and then additional auxiliary parameters. So I'll try to do this live demo. This is my first, so please be patient. So I'll just start by drawing a curve or two curves in Rhino. And this one will become the directrix, and this is going to be the generatrix. And I'll rotate this one. Sorry. The computer has a slightly unusual location for me, so, but yeah. Okay, so now this is a generatrix that is in a plane perpendicular to the directrix. But this is not a prerequisite. This is currently a coincidence. So, and I will access these curves by setting them from the Grasshopper viewport to here. And now you can see, hopefully, it's just a little bit. So if I click on this component and I select it, it should show the excess geometry here. So this is like the green curve over here. And I'll also like set this curve on this side, to also have it ready in Grasshopper. I'll just for convenience purposes, I will reparameterize both curves to be parameterized in the domain between 0 and 1. This can be done quite conveniently just by a few clicks. I'll now, because this component takes a polyline as input, I will just sample this curve by defining a range. So this can be done quite conveniently with another component. Here, this is the domain of the range and the number of samples or steps. And here I want to have somewhere between 3 and 100 samples because we will just play with it. So as you can see, the output is currently a list of 4 values. But yeah, I can just increase the number of steps and it will make the resulting list longer. And now I can evaluate my curve at those points, at those parameter values, and get a sampled curve. And you can see I can vary the number of samples. And I'll do so also for the directrix, but I'll choose a lower sample count for that one. Okay, so now we're ready, hopefully, to connect these polylines to this component, and we'll see the default construction of a Monge surface. I'll just hide these points because I won't need them much later. Okay, so this is now a Monge surface. To make this into like a non-trivial conet, I'll need to add apex locating values to it. And I'll need to add them each for the value of my directrix. So one way to do this, there are multiple ways, but one thing that I find intuitive is to use the rich graph mapper, which essentially lets you choose a graph. I will choose interpolated with 5 points, and I'll just modify it so that the construction doesn't explode by default. And I'll choose this list as the set of values, input values, and I'll set the target, because I would like to have the values somewhere close to 1, I'll just set the target to be between 0.75 to 1.25, I think. This should be better. And now you can see that these are my apex locating functions that are values that are sampled from this graph. Okay, so what happens now if I connect it to the component? We incorporated in our implementation, we incorporated a couple of additional functions that I will just disable for now, just for illustration purposes. I will disable the normalization, and I'll just use these apex functions. Okay, this looks better than expected, but we can play with this, and we can see that we can easily bring this to break. And another thing, or explode. And another thing that is maybe a little bit disadvantageous is that if I change the number of samples here, it will influence greatly the shape of what I'm getting out. And the reason for this is that just using the construction as presented before, this is not scale independent of the edge lengths of our polyline. So what we added as a feature instead, we added this normalization approach where we can normalize these values to at least get something that behaves more regularly during refinement in one direction, like this. You can see the outline almost doesn't change once the sample size is high enough. Yeah, and everything is still highly interactive. So, oops, no, sorry. Yeah, oh, okay, never mind. Yeah, here, those are the control points. Yeah, so we can move things around, and the geometry will deform accordingly. Another thing that you might notice is that the outline here does not quite correspond to whatever is going on here. Like, yeah, this doesn't seem to be quite useful for design. Like, for example, this one, here we have like, yeah, this peanut shape, but it's not quite reflected here. So what we added as an additional functionality is we have a mapper that maps this graph into like apex locating functions that should resemble this graph more when it comes to the outline of the shape. So the corresponding component is called CNets values to apex function. So here I'll need to set this to false because this is, you can see this is just like breaking the thing, and now I'm just going to, yeah, to connect this, and now it's a little bit better. I'll just remove the scaling. Now it behaves much better, and you can see it's much more intuitive to modify the outline of the CNet now. Okay, so this is one type, like one aspect of this generalization. But we have this other aspect of this generalization by changing this construction planes. Here, for this, we will access this through the input ratios. I don't want to go into detail here, but I think that just showing it will be hopefully a little bit more intuitive. So for this, I'll again use graph mappers. For this one, I'll just use 3 points. I'll start with values that are close to 0.5, and I'll use 4 copies for each of the points of the generatrix individually. So here, and I'll end mine, and I'll just connect this. This is just like some internal data structure that Grasshopper is using. And oh, and I should have connected these values. So now I'm just going to connect. Oops. And I broke this one, and I need to remove this. Okay. So now we're ready to see the influence of ratios. Nothing happened much, but if I want to change the outline of this shape, let me maybe go to a slightly more discrete version of this. I can influence it by, again, moving here these parameters. And if you want to learn more about the relationship, the actual relationship between these parameters and the shape, you can read about this in more detail in our AHG paper. Yeah, so as you can see, I can address like each of these curves individually, and yeah. And I can still like increase the number of samples or decrease them. Yeah, I can modify this curve and it will propagate nicely. Okay, another thing that I mentioned during a few minutes ago is a support structure, torsion-free support structure. So we have a component that, or actually more components than one, but like I'm going to show you one of them. This one, where we can take the CNet, the corresponding directrix, and just generate this support structure. And still everything remains interactive and real time. Yeah. And yeah, we can also change this scale factor here. So when it's 1, when it's 0, it's like going all the way through to the directrix. Sorry, there's a fly. Otherwise, yeah, otherwise it moves a little bit closer to the mesh itself. We have also a few methods that can be used for the actual fabrication of these meshes. So, for example, we can unroll strips, which is also, like, this is just like a convenience method to, yeah, so the unroll method is this one. Yeah, it's not magic, but still convenient if you want to fabricate things. Maybe I'll use smaller than 20, and we can just like move them by a distance and separate them for fabrication. We can also use the PQ mesh, explode it into different strips, and then unroll these strips individually. No, this is a transformation, sorry. I want this component. So yeah, here I separate this mesh into strips, and then I unroll the strips here. And again, these can be then readily used to laser cut and stuff like that. And we can also just like still like increase the number of samples. Okay. Are there any questions? Sure, David.
So you started here with smooth splines, and then you had to sample them to be able to do this construction using planar quads. Can you algorithmically operate just directly on the splines and make semi-discrete strips?
That's a very good question. So when the directrix is smooth, the resulting construction involves solving differential equations. And I think currently just going with the discrete counterpart was more convenient. And we figured that because there's like this very nice behavior towards the refinement, it will not be, well, it is, at least for most applications, good enough, because you can then, like, if you sample high enough, you can then still interpolate, and like maybe that's even more convenient than going through the hassle of solving differential equations. Yeah, but we do also, so for a bunch of examples, I was very inconveniently using Mathematica to solving those differential equations there numerically. But yeah, for the design, it's not very useful. But yeah, the good thing is that like we can go smooth then in both directions. This is then a system of partial differential equations, and this is then also nice. Yeah, but yeah, we can also like increase the number of subdivision here in the other direction as well. Whoops. Okay, I don't know.
Oh, because you have this
ratio thing on. The ratio. Okay. Yeah. Oh yeah. So maybe if I turn this off. No. Yeah. Okay. Yeah. Thank you. Yeah. This is now with the support structure, but yeah, it's converging towards something smooth. Okay. Oh, yeah, sure. Was this all from my side? I forgot. Oh no, there are some examples. So, so at least with the modifications we made, like regarding the like implementation, we got good feedback by test users. So Florian, the architect in our lab, designed this glass facade. He also experimented with approximating a catamaran with developable strips. For this, he approximated 1/2 of like a boat part of this catamaran by a CNet, you can see, and then reflected and added the other parts. Here you can see that he used these like additional functionalities of those non-planar generatrix aligned curves to like really get the shape that he wanted, especially in this area of the especially in the area of the tip of this boat hull. And also very recently, a student at ECAL named Finn Johnson used this implementation for his final project, and he designed this bike frame with our implementation. And yeah, so if you wanna like also explore this implementation for your applications, you can download this plugin here, and yeah, you can share feedback with us, and yeah, and I'll let Michele do the rest.
All right. Thank you. Thanks, Klara. So I see we're slightly tight on time. I will just want to take now some 15 to 20 more minutes to show you some results that we obtained with the ConeNet construction and deploying optimization on top of our construction. So I want to show how we can integrate high-level geometric objectives and then compute the cone nets that achieve those objectives. Quick recap first. The cone net construction is a mapping that takes as input a directrix, we call it X, a generatrix G, the plane normals that we call P, and the apex locating function A. And this construction returns a cone net in the form of a PQ mesh. As we've seen, these input primitives influence the shape in ways that we can control in the interactive design tool. But how can we control high-level geometric features, like, for example, the cross-sectional shape at the end of our cone net? So these are features that we measure on the output mesh in what we call performance space. While the knobs, the knobs, the variables that we can tweak and tune, are live in what we call design space here on the left. So before showing some results that we obtained via computational design, let me start from a very simple introductory example that explains this paradigm. So imagine this simple setting. We want to throw a rock and hit a specific target. So the first thing that we can try to do is attempting a throw and seeing where the rock lands. In our digital setting, the outcome of this throw can be easily computed because we know the equations that describe the parabolic motion of the rock. One can then adjust the outcome by varying, for example, the force. So if we throw harder, the rock will land farther. And another parameter that can be independently varied is the throwing angle. So force and angle together define our two-dimensional design space in this case. To measure how far we are from the target, it is enough to consider the distance between where the rock lands and where the target is set. This is what we call performance space, and in particular, the distance is our performance metric. Right, so it is now, we can now consider any point in our design space, any parameter value, and compute the landing point of the rock, and evaluate then the performance metric in the design space at every point. This will give us a scalar function that lives in the design space, and it is now easy to see that the values of the force and angle that would give us a perfect hit correspond to selecting any of those points on the blue curve. So to recap, we have two spaces, design and performance. There should be two arrows over there, one on the top that goes to the right, and another one that comes back. A forward model connects the two spaces, and during inverse design optimization, we use information from the performance space to update parameters in design space. So this global picture can be a bit misleading, though, because in this simple case, we could easily compute our performance metric everywhere, but in general, we do not have access to that kind of information. So when the design space gets higher dimensional, like with our cone nets, then the global picture is too expensive to compute, and we need to optimize our construction computationally. So to make this more concrete, consider this example for a performance metric. A Monge surface with a closed directrix and generatrix is not in general a closed surface. This is because Monge surfaces are generated by a rotation minimizing sweep. So rotating the generatrix also doesn't change the angle difference between the initial and final profiles. So this mismatch is what we want to minimize, because corresponding pairs of points in the two profiles should coincide, and we then use a pairwise distance as our performance metric. If we want the surface to close flush, we then have to tweak the design parameters to make that happen. Let's assume we want to work just within the space of Monge surfaces, so we constrain our design space and performance space to Monge surfaces. In particular, this means that the planes and apex locating function values are off limits. We can't touch them because they are given by the construction already. And we have also seen how changing the generatrix doesn't help. So the only degree of freedom that we have left here is X, which is our directrix. That corresponds to our design space down there. So let's look at how that works in practice. So here there is a Monge sweep with end profiles that do not match. And on the left here, you see some slightly washed out unrolled strips. So to optimize this structure, we parameterize our directrix using a cubic spline that interpolates the point Q, and then we optimize Q in such a way that the directrix X remains close to the initial target, which is a truffle curve in this case, but also that the ends of the tube align using the metric that we have just seen. So as we minimize this functional, then the tube closes up smoothly. You can see it over there and also in the change in the strips. The change is subtle, it's going to play again now, but this change cumulated over the whole sweep will give us the closure that we were looking for. We then split the strips in a few parts each, and we nested them together to fit our laser cutter. We cut the strips, we assembled them, added a neon tube inside, and now this lamp shines in our lab. So now what if we wanted to preserve the shape prescribed by the directrix, so we don't want to touch the directrix anymore, we can then freeze X and we have to unlock other degrees of freedom, for example, the plane normals here. I'll now show an example that illustrates how cone nets broaden the design options compared to Monge surfaces, which is our initial claim. So Maika and Scholz recently presented a method to construct Monge tubular surfaces. They are interested in families of tubes whose directrix wrap around a torus, which now we know in most cases do not close up. So what the authors do is they use bisection to select one specific such torus that guarantees the tube closure. So this works in this specific case, good, but in all the other cases in which the ratio between the torus radii does not match the value found by bisection, the Monge construction results in an open surface. With the cone nets, we show that by optimizing only the plane normals P, so here we're keeping the directrix frozen to whatever curve is prescribed by the geometric construction that we use initially, we can generalize all of this computation and find a smoothly closed piecewise developable surface, also for all the other shapes. Now, if we look at the unrolled strips, we can also spot another major advantage of working with the cone nets, because the Monge strips are all different. So here we have a square cross-section, so we have 4 strips, and even if at first they look similar, they actually are not identical. And we can understand why by looking at 2 curves. So we have the directrix over there, which loops around the major axis of the torus 7 times, forming 7 lobes. And then we can look at the curve that follows a ridge of the tube, so that follows the connection between 2 neighboring strips. This curve loops around the directrix for 3 times until it closes up on itself. So for each of the 7 lobes, we end up having 0.43 rotations, which makes 4 different strips. Now, when optimizing a cone net instead, what we can control is also the number of the turns the ridge curve does around the directrix. So if we set that number to be, for example, 1/2, such that each lobe has exactly half a turn, then the resulting structure becomes self-similar and the strips become modular. Again, this is true irrespective of the specific curve we're using as directrix, and we can see that here all of the strips, the 4 groups of strips generated by Monge are all different from each other, while at the bottom we always get modular strips. And in terms of design advantages, modular strips can be more easily fabricated, assembled, and then replaced if needed. When designing with developable patches, one thing to pay attention to is the edge of regression that we have seen before. So consider this simple discrete patch. If the points where the rulings intersect fall outside of the boundary of the patch, then it's all good. But if a singularity falls within the patch, then the resulting strip can have foldovers that correspond to non-physical intersections. So if we zoom into what is happening here, we can see that one of the edges of the patch boundary, the red one, is flipped with respect to the direction that is prescribed by the directrix tangent. We fix this in the following way. We measure the signed length of the red edge vector, which is positive if it's aligned with the tangent, and negative if flipped. So in this case, it would have a negative value. And we then penalized negative values of L. So that's the penalty function that we use that pushes the construction towards configuration without intersections. Note that for values that are above a certain minimal edge length that we call epsilon, that we find numerically acceptable, above that value, the penalty is exactly 0, so it doesn't contribute to the design. Right. So we can see how that helps us here in this case. We consider this tubular Monge structure in which a sharp band of the directrix generates some self-intersections. And by activating the term that we have just seen and optimizing the planes, we can remove the intersections. However, we can spot here that the shape now looks a bit different. And this is because we are still constraining our generatrix-aligned curves to be planar, so to remain planar. And there is a displacement of the rulings that happen down there at the bottom to resolve the self-intersections, but that deforms the structure there at the top. So if we relax that constraint and use multiple planes, so here we use 4 planes for the 4 points of our cross-section, then we see how the rulings can now change independently, and they will get modified more at the bottom region, resolving the self-intersection, and are preserved at the top, obtaining a better shape preservation. Another thing that coordinates can do is approximate surfaces with variable width. So if you consider this smooth surface, having the shape of a Klein bottle, we take that as reference. We can then measure its cross-sectional diameter, d bar, and we use it as target. We prescribe it as target for our coordinate that we want to optimize. Here we then concurrently optimize the plane normals P and the apex locating function A to obtain a piecewise developable approximation of the original smooth surface. To validate the results, we then built a physical model out of paper strips that confirms that the geometry of the strips effectively encodes the final shape of the coordinate. Another example that displays scaling of the generatrix is this design study for a lighting fixture that was done by Florinis Voreno and optimized using our framework. The idea here is to leverage the fabrication simplicity granted by developable strips to assemble an inexpensive mold for freeform casting that could be considerably cheaper than, for example, 3D printing or milling the mold from a solid block of material. The orientation of a strip can also contribute in defining the function of a coordinate. So to model this concept design of a rocking chair, we allow the designer to prescribe target strip normals at the headrest and seat regions, as well as along the rockers to guarantee continuous contact with the ground. Similarly, as before, we added a penalty term to the objective function that aims at aligning strip normals to the prescribed target, and then we optimize the planes and the apex locating function. What you're seeing here is the final result that shows how the optimized quad normals align well with the additional geometric constraints that was prescribed by the designer. As last, one insightful stress test for our method was to consider a minimal surface with non-zero Gaussian curvature, so then not developable, and try to fit one of the developable patches of a coordinate onto this surface. So we set up the following geometric objective. We require one of the boundary strips to be aligned to the surface by minimizing the distance ds, here in red, while an adjacent tube ridge is attracted to the surface boundary by another term. When no surface attraction is present, so when the weight W is equal to 0, then the tube remains close to the boundary because the strip, the red strip, has no incentive to align to the surface. But as this weight increases, then the tube slides toward the central region of the surface, which has lower Gaussian curvature, and it's then in some sense closer to being developable. This allows trading off boundary attraction for surface tangency. This example shows once again how prescribing high-level geometric objectives in our pipeline allows using computational design to design coordinates. Okay, so we have seen multiple objectives prescribed in performance space and the resulting connets obtained via inverse optimization. There are other aspects of this construction that make it particularly appealing for design, and let me give just a very quick overview of two such properties that we just started exploring and we believe have great potential for computational design. So the first property is this. The connet construction, as we formulated it, is a non-injective map. So there you see one point in design space, one in performance space. There is an arrow that connects the two. But to get to that point, we can also pick other design parameter values. So for any connet, there exists multiple, in fact, infinitely many parameter values that encode the same geometry. But even if the resulting PQ mesh is always the same, the construction, these two constructions, so infinitely many, are not equivalent, and each can be more or less desirable depending on the setting. Let me explain why with an example. Consider this connet, which was obtained with a specific choice of directrix, generatrix, planes, and apex locating function. Now we can identify the cone epices and imagine freezing them in place. It turns out that we can also find other sets of design parameters that give us exactly the same connet. So there you can see the directrix changing, and these two connets that are exactly the same in terms of meshes, but so what's the difference here? What changes? Why is this interesting? Because, for example, the support structures that are associated to these two connets are different. So this can be extremely useful in optimization to set secondary objectives on the support structures. So among the many equivalent parameterizations of a connet, one might prefer the one that is associated to a specific support structure. And why? Because in architecture, as we've seen before, we know that higher stiffness might result in better structural performance. And another criterion that can be used is the use of material, for example. So, for example, if the flat strips nest optimally in the plane and allow fabrication with minimal with minimal material waste, that would be another desirable target. So our computational pipeline allows adding any sort of custom objective terms to encode these and possibly other goals. Now let me conclude with the other property I want to briefly touch upon. We have seen that connets, especially tubular ones, usually make for stiff structures. And one choice of design parameters corresponds to one stiff connet, especially if it's tubular, that will resist deformation under external loads. There are, however, some special subclasses of structures that behave very differently and are instead flexible. So they're not stiff but flexible. A flexible structure corresponds to a family of 3D states that all share the same building block. So in our case, they all share the same strips. And in such flexible PQ meshes, the geometric constraints do not fully lock neighboring quads, but guarantee one or more residual degrees of freedom that deform the discrete surface while preserving quad planarity. Our optimization framework can be applied to all the classes of flexible meshes that belong to the broad family of connets. So we can design, for example, these optimized structures that are modular and closed, which would be hard or even impossible to do by hand. And these structures are flexible. So many research questions remain open here, including how to better analyze, control, and design not only the final shape, but also the deformation path of our flexible mesh. But overall, combining the understanding of flexible structures with a computational inverse design pipeline could, in the future, let us push the boundaries of developable structures, deployable structures, even further. And here you see some examples that have been achieved in the past in terms of folding and deployability. With this, I want to thank you very much for the attention. And I think we don't have any more time for questions, but thanks again for the previous ones. And if you want to come downstairs and have a look at the models or chat, we'll be here. Yeah, let me say it out loud. Thank you very much to Quentin, Marc, and Florine, who were our co-authors for all the works that we've been talking about today. There is a QR code over there, brings you to our webpage. There is